So last day we have stopped at evaluating the convolution integral, right? You have noticed that if I have LTI system, something like that, one LTI system with say impulse response h of t, and if this particular system is excited with a signal x of t, then the output y of t is given as the convolution between x of t, the input which you have applied, with the impulse response x of t, and that is the convolution sign with h of t. So basically the convolution operation is nothing but you have Fourier. So it's a combination of 4 defined operations, right? One was folding, then you have shifting, then you have the multiplication, and then you have the addition, right? So you have like x of tau, h, t minus tau. So when I write like h t minus tau, then you have already got the folding from minus tau, and t minus tau means shifting, and this x tau multiplied with that, that's the multiplication operation. So folding, shifting, multiplication, and then you have this addition, d tau, going from minus to plus infinity. So that is the generic expression for continuous time convolution. Y of t is equal to x of tau, h t minus tau d tau, integration from minus to plus infinity. On the other hand, we have a discrete time system, in which case the signal, the impulse response is given by h of n. In that case, this output for a discrete time system. Similarly, for a discrete time system, you can write y of n. So you should have a summation instead of integration. Say x of m, h of minus m, where m is ranging from minus to plus infinity. X of m, h of n minus m, m is going from minus to plus infinity. That is the output sequence for a discrete time system. So convolution is basically an operation between any two signals. So if you have one signal, say x of t, or x1 of t, or another signal like x2 of t, you can always perform the convolution operation between two signals. Nobody can stop you. Just like other operations, just like addition, just like multiplication, just like division, you can always perform the convolution between two signals. Okay, but what is the speciality for this convolution in case of signals and systems? So when we deal with an LTI system, you understand what is meant by LTI, linear time invariant system. And linearity means, as you know, it's a combination of additivity and homogeneity, right? Additivity, homogeneity, and the time invariance. So all these three properties are embedded in the LTI system. And in such a case, the output of such a system can be viewed as the convolution between impulse response of the system and its input signal, right? So output can be obtained by performing the convolution between the actual input and the impulse response, and that is the beauty of the impulse response. So what is meant by, or what is the significance of impulse response, or what is the significance of rather this LTI system? So LTI system, or linear shift invariant system, or linear time invariant system in particular, so these systems are such a system for which you can know everything about the system just by performing experiment of the system. I would like to know everything about the system. I would like to characterize the system. That means what? For any input, I'll be able to find out the output. That is meant by characterization. I would like to know everything about the system just by performing only one experiment. What is that one experiment? Just excite the system with an impulse input. Delta t for continuous time system and delta n for the discrete time system. Just excite the system with this impulse input and find out the response, which we call like impulse response. And once you do that, then you will be able to characterize the system. That means you know everything about the system just by performing only one experiment. And that is the best thing that you can do. You know everything about the system by performing the minimum task. Only one experiment because you cannot do any experiment less than one. At least you have to perform one experiment. And that experiment is finding out the impulse response of the system. Okay, and this impulse response will get, because already you have seen that we have in the previous chapters, we have found out that types of characteristics resulting from a system. Like you have noticed some memory-based system, memory-based system. You have noticed like a stable system, evo-stable system. You have noticed like the causal system, non-causal system, anti-causal systems. So all these characteristics of the systems can also be visualized just by observing the impulse response. So impulse response is something that will give you the entire picture of the system itself. Impulse response will give you the entire picture of the system itself. That means it can completely characterize the system, and that happens only for LTI system. You can also calculate the impulse response for non-LTI system as well, because nobody can stop you. Suppose you have one non-LTI system, right? Non-LTI, either non-linear or non-time invariant or both. LTI means what? Linear as well as time invariant. Non-LTI means what? Either non-linear or time invariant or both, like non-linear as well as time invariant. Right. So for those systems, you can also calculate what is the impulse response. Nobody can stop you because you have some. Can you give me some example of a non-LTI system? Non-LTI. Just give me an example of a system which is non-LTI. Just tell me the input-output relationship. Just tell me the input-output relationship.
So cos x.
Huh?
Cos x.
Okay, phi t is equal to cos of xt. Phi t is equal to cos of xt. That's great. So, suppose I provide, in case of xt, I provide delta t. Okay. So, I'll be getting something. That is basically my impulse response. If xt is equal to delta t, this y t is equal to ht. So, even if the system is non-LTI, then also you can also calculate what is the impulse response. But that impulse response will not characterize the system properly. This characterization is possible if and only if the system is LTI. You cannot know everything about the system just by performing only one experiment for non-LTI system. Okay, so now let us move to, after observing a single system, now let us move to a case where we have a cascade of system, something like that. Suppose one in parallel path and the other one is in series path. Let us consider you have one system characterized by this impulse response h1t, and you have another system characterized by this h2t. X of t. This is y of t. I assume that both of these two systems are LTI, right? So that's why I have used this h1t and h2t, because until unless the system is LTI, the impulse response doesn't carry any significance, right? Until unless the system is LTI, the impulse response doesn't carry any additional significance. Okay. So what we have over here, you have the signal x of t, and you have a combination of two systems, h1t, h2t, they are in parallel, right? And then the output of these two systems are added together to find out the final output, y of t. Now the thing is that how can I find out the overall impulse response of this system using this h1t and h2t? Is the block diagram clear? X of t is the input and you have two different two different LTI system, which are characterized by the corresponding impulse responses H1t and H2t, and accordingly the outputs are obtained over here. So let me call this output is equal to, say, let us call this output as Y1t over there, and here you have this output as Y2t, right? And the final output is the summation, can be summation, can be subtraction as well, plus or minus, doesn't matter. And Y of t is equal to Y1t plus Y2t. So now I would like to observe, okay, since you have this entire thing, so now I would like to visualize this under a black box. This under a black box. The input to the black box is x of t. The output coming from the black box is y of t. Inside you have these two systems, H1t and H2t. Now I would like to find out the overall impulse response by virtue of this H1t and H2t. Can you get the point? It's pretty easy, as you know. Y of t, so what is y1 of t? How can I write down y1 of t? How is it defined? Y1 of t. What is that? Xt convolved with h1 of t, right? So I can write like x of t convolved with h1 of t. That is basically minus to plus infinity. You can write like x of tau h1 t minus tau d tau. What is y2 of t? Y2 of t is equal to xt convolved with h2t. Similarly, you can write like minus to plus infinity x of tau h2 t minus tau d tau. Okay. Then what is the final output y of t? This y of t is basically the summation of y1t and y2t. So now you see the summation is done from minus to plus infinity, so the limit is same, and it is this integration, it's not basically the summation, integration. Over here you have a summation and then you have an integration over there. Integrand being the same, x tau over there, x tau is common, so you can take it common. So what you have, minus to plus infinity x tau, then what you can write, h1 t minus tau plus h2 t minus tau d tau, right? So this h1 t minus tau plus h2 t minus tau, you can visualize this as h1 t minus tau plus h2 t minus tau. You can consider this as, say, h t minus tau, which is equal to h1 t minus tau plus h2 t minus tau, right? So then I can write this as minus to plus infinity x of tau, or you can also write like h1 to t minus tau to make sense, h1 to t minus tau. So x tau h1 to t minus tau d tau. X tau h1 to t minus tau d tau. So what is this h1 to t minus tau? This is h1 t minus tau plus h2 t minus tau. So if you have two systems running in parallel, one is h1t and second one is h2t, then the equivalent system, you have two systems, h1t over there, h2t over there. I mean, these are the impulse response of those systems, h1 LTI systems, h1t and h2t. Now, if you would like to find out the equivalent system, I don't want to have these two systems and the summation outside. I'd like to have only one system. Instead of having these two systems and the summation sign over there, inside this dotted black box, I would like to have only one system, right? And what I mean to say is something like that. I would like to have x of t there, one system there, x of t there, one system there, which I call say h12t, and that will produce the same output y of. Okay. Instead of having this h1t, h2t and the summation, it will perform the same operation. So what is it? What is that equivalent system? What is the equivalent impulse response? So that equivalent impulse response basically the summation of these two, as can be verified from the mathematics itself. Can we get the point? If you have two systems running parallel, so you can have multiple systems. Not only two, you can have multiple systems. You have n number of systems. H1, H2, H3 up to Hn, and all of them are summed together. Okay, then what is the equivalent system? I don't want to have all these systems separately, I take only one system. Right? So that is basically the summation of this, summation of the impulse response. H1 plus H2 plus H3 up to Hn. Can be minus. In some cases can be minus also, some H1 plus H2 minus H3 plus H4 minus H5 and so on. Is it okay? That is one part. So here what you have seen, you have like the same input is being fed to the two systems. H1t is receiving, this system characterized by H1t is receiving xt. This system characterized by H2t is also receiving xt. And their final output of the system is basically the summation of the individual outputs. Now let us consider a system something like that, where you have this kind of scenario, like you have this system x of t, then you have the first LTI system characterized by its impulse response h1 of t, and then the output of the system is being fed to the second LTI system, which is characterized by h2t, and then finally you are getting the output as y of t. This is known as the cascading of the system. We have one system, first system, whose impulse response is given by h1t, the second system, whose impulse response is h2t, and the first system, then you have the second system h2t. You can have multiple systems after h2t as well, and then you are getting the final output y of t. Okay, so I can consider this output, suppose this output is z of t, intermediate output. Okay, so now the question is, what is the relation? Now what I want to say is, suppose I don't want to have these two systems. Instead, I'd like to have only one system. I'd like to replace. You have two systems connected in cascade, something like that, and I'd like to replace this by a single system. Instead of having this h1t, h2t cascade, I'd like to have only one system. Okay. So impulse response of that system. So whenever I refer to system in this lecture today, remember that the system is LTI. Whenever I am referring like h1t, h2t, something like that, whenever I refer impulse response, remember I refer to LTI system only. Okay. So you have two system over there, h1t and h2t. Then I would like to replace this by a single system. Okay. So what will be the impulse response of that newly constructed system? What is the formula there? So ZT is basically what? ZT is basically the convolution between xt and h1t. And what is y of t? Y of t is basically the convolution between zt and h2t. So this can be written like xt convolution h1t, and then you have h2t. Okay. Now I would like to find out one system out of this h1t and h2t. I'd like to find out one system like so. You have given xt as your input. I would like to find out only one system. Say let it be say h12t. When it receives the signal x of t, it will produce the same output y of t. That means the equivalent system. I'd like to find the equivalent system. Initially, I have two systems, h1t and h2t. And what is the, so instead of having two systems, h1t and h2t, I'd like to find out only one system that will perform the same job, equivalent system. Right? So when it receives the signal as xt, it will produce the same output as yt. Now the question is that what is the relationship between this h1t, h2t and h1t? Is the problem clear? So now let's check it. Okay, fine. So you know zt, I can write zt as convolution between xt and h1t. So I can write like minus 2 plus infinity x of tau h1 t minus tau d tau. Okay. And what is y of t? T is equal to the convolution between. So I can write like let it be zm h2 t minus m dm. Clear? Yt is what? Yt is basically the convolution between zt and h2t. So minus to plus infinity zm h2t minus m dm. Just change of variables only over there, right? So what I can write over there? Here you have minus to plus infinity. So how zm is defined? Zt, you know, zt is equal to minus to plus infinity x tau h1 t minus tau d tau. So in case of zm, what I can write? Minus to plus infinity x of tau h1 m minus tau, then you have h2 t minus m d tau dm. Is it all right? Any doubt up to this? Just the change of the variables and all. Yt is basically the convolution between zt and h2t. So I can write like integration from minus to plus infinity zm h2 t minus m dm. Right? Zm h2 t minus m dm. And zt, you know, zt is basically the convolution between the xt and h1t. So I can write like minus to plus infinity x tau h1 t minus tau d tau. So what is zm? X tau h1. In case of t, you can just replace this by m. So h1 m minus tau d tau. So x tau h1 m minus tau h2 t minus m d tau d. Is it all right? Okay, fine. So now I have to find out the expression in this form. So you know that y of t, you have over there minus to plus, you have to double integration over there, minus to plus infinity x tau h1 m minus tau h2 t minus m d tau dm. So now what you need to do is that you have to change the variables, right? So put the variable like let's consider this t minus m. Let's consider over there. Better if I go to the next slide. So I of t minus 2 plus infinity. Then we have another minus 2 plus infinity. What was there? X tau h1 m minus tau is to t minus m. Without dm minus tau t minus m. Okay. So first of all, what you can do is you just consider this. You just change the order of the integration. So here you have two different variables. The integration is performed on tau and then m, d tau, dm. So you can change the order of the integration. And the limit of the integration being the same from minus to plus infinity. Minus to plus infinity for tau as well as for the m. So let's consider this one minus to plus infinity. X of tau there. I'm changing the order of integration. So here it says that first you integrate over tau, then you integrate over m, d tau dm. What I'm doing here, because as you know the integration is a linear operation, so you can change the order of integration always, that's by summation. So first I integrate over m and then I integrate over tau. So that's why x tau is taken outside. So this integrations, so this limit is for tau. Here this limit is for m. This limit is for tau. Then you have minus to plus infinity h1 m minus tau h2 t minus m dm and then d tau. Yeah?
H1 t minus tau. H1 of t minus tau.
H1
T minus tau. Zn.
h1 m minus tau h2 t minus m. h1 m minus tau h2 t minus m. What is the fault? I've just copied from the previous slide only. We have x tau h1 m minus tau h2 t minus m. X tau h1 m minus tau h2 t minus m d tau dm. Any confusion in understanding this one? Basically what is done over there, this is for, when I write like this now, this variable is for tau and this variable is for m over there, right? So I've just changed the order of integration. So first to integrate, so as far as the first line is concerned, first to integrate with respect to tau, then we integrate with respect to m. So here what we have done, this is with respect to tau, this is with respect to m. Just have changed the order of integration. So therefore this entire thing up to this, it's not a function of tau. It's a function it's a function of m only altogether, right? So now what you can do is you have to change the variable. You need to change the variable now. how to change which variable I should select over there. I have to replace. I have to change one variable by another. Which variable I have to select? T minus m. So t minus m, suppose I select the t minus m, say t minus m, let's put t minus m as a new variable, say n. Right? So t minus m is equal to n. Therefore, so therefore dm is equal to minus dm. Done. T minus m is equal to n, so dm is equal to minus dm. And the integration will be from minus for m. If you see over there, the integration, the range for, over here it is from minus to plus infinity. So when it becomes like t minus m is equal to n, it will be from plus to minus infinity. And if you just absorb this minus sign, then once again it will be from minus to plus infinity. Okay. So what I can write over there is, this is minus to plus infinity, that remains unchanged for tau, x of tau. Then you have, as I mentioned, the limit is from minus to plus infinity for m, but for n it will be from minus to plus for n it will be from plus to minus infinity, and there you have minus dn there. So if you absorb them, once again it will be from minus to plus infinity. Minus to plus infinity. Remember, this is for n. This is for n, not for m. Okay. Well, h1. What should I write over there? h2 is okay, all right. h2 is all right. h2 what? h2n, right? dn there. T minus m is equal to n. So h2n dm is equal to minus dm. Minus you have already absorbed. That's done. So what will be m minus tau then? M minus tau. M is how much? M is equal to t minus n. M is t minus n, isn't it? M is equal to t minus n. So t minus n minus tau. And then you have d tau there. Any problem in understanding? Just the change of variables, nothing more. Take time to absorb the concept. Just simple integration and change of variables, both there. The first integration, once again, it is for tau. This integration, this limit is for tau, and this is for n. Now, if you just take a look at this one, this thing inside this bracket, what you have basically, is it a known form to you? h2 of n multiplied with, is it a new thing? Minus to plus infinity h2 of n h1 of t minus tau minus n dn. Have you ever seen this kind of integration? h2 of some variable, h2 of n multiplied with h1 of t minus tau minus n dn. What is that? Convolution. Evaluated at where? Evaluated at t minus n. What is the formula? x1 of tau, x of tau into h of t minus tau. X of tau, x of tau, h of t minus tau. So here you have x of n, h of t minus tau minus n. Right? So this is basically the convolution. And you know that convolution operation is a commutative operation. So convolution, last we have already established this one mathematically, that h1 converted with h2 is also equal to h2 converted with h1. Right? So basically what you can see over there is, this is h2 convolved with h1 at t minus tau. Right? So I don't have space over there. Anyway, let me go to the next slide. So y of t, I have found minus to plus infinity, x of tau there, and what else? Inside this bracket, what we have? This one, h1 t minus n minus tau to h2n tn. That means what? I can consider the entire thing as the convolution of, so I can write this as, this entire thing inside this bracket as h12 t minus tau, h12 t minus tau, where simply h12 t minus tau. D tau, where h12 t is basically the convolution between h1t and h2t. So h12 t minus tau is basically the convolution between h1t and h2t at t minus tau. Right? Now is it known to you? The second one? Another convolution. Right? Now what we are looking for? We are looking for a system. We know that I would like to find out one system h1 to t for which if the input is xt, the output is yt. Right? And we have already arrived at this point. We have found that output yt can be written as the convolution integral between the two signals. One is your x of t input signal, and second one is your impulse response h12 of t. So that's why x of tau h12 t minus tau. So therefore, what is the relation between this h12 t with the individual h1 and h2 when the two systems are connected in cascade? This is basically the convolution. Last time what we have seen, if the two systems are connected in parallel, then the equivalent impulse response is basically the summation. And when the systems are connected in cascade, right, then the equivalent impulse response is basically the convolution. So this is basically, as we have already mentioned, this is equivalent to h1t convolved with h2t. Or you can also change the order of this. You can also place h2 first, followed by h1, or h1 first, followed by h2. Because as you know, this operation is a commutative in nature. Right? h1 convolved with h2 and h2 convolved with h1 will give you the same result. So these are some of the properties of the convolution. Just like addition, as we have mentioned that okay, addition is a commutative operation, multiplication is a commutative operation, but not the division, not the subtraction. A plus B is equal to B plus C, but A minus B is not equal to B minus C. Isn't it? So just like convolution is a commutative operation. A convolved with B is same as B convolved with A. Right? So this is commutative in nature, it's also as well as it is distributive in nature. Okay, so with this basic discussion on the operation of convolution, now let us throw some light on the properties of a system by observing the behavior of, by observing the impulse response of that particular LTI system. Having noticed that these LTI systems, they are characterized by the corresponding impulse response. So already we have defined different characteristics of any system. The first one was a memory-less system we have mentioned at the very beginning. So whenever I say anything about the system, remember this is all applicable for LTI. All of them are applicable for linear time invariant system. Because at that time I have told you that linearity, time invariance, stability, memoryless, causal, non-causal. So these properties are independent of each other. A system can be linear, can be stable, but not causal. A system can be time invariant, but not stable. The system can be stable, but not memoryless. So these different properties, they are interdependent. They are not interdependent. They are independent of each other. Only there are two properties which are interdependent to each other, which are known as this additivity and homogeneity. And when they are connected together, then only can have a linearity, but not always. If additivity and homogeneity are coming together, then we call the system as a linear system. If not, then it's a non-linear system. But all the properties, they are independent of each other. So now let us focus on LTI, linear time invariant system, and based on that, I would like to find out how, using the impulse response of the system, we can characterize the different types of systems. So let us have the memory-less system. So can you remember what is the basic property of any memory-less system? Let's start from the discrete time system. That will be easier for you to understand. When can I call a system a memory-less system?
It was to exploit.
No. When? What is the criteria? We are giving some example.
Is dependent on present.
Output depends only on the present input. Only on the present input. Not on the past, neither on the past, nor on the future. Okay. So for example, and since the system is LTI, let us take some discrete time system, for example. So you know this output y of n can be represented as x of k, h of n minus k. K is going from minus to plus infinity, right? That is true for any LTI system. Yes or no? So now I can write something like that, plus x of say minus 2 h n plus 2 plus x of minus 1 h n plus 1 plus x of 0 h of n plus x of 1 h of n minus 1 plus dot dot. Can I write like this? Yes or no? Yes. I can write. Now the thing is that the output y of n, it will depend only on xn. Or in other words, I can also change it to some extent. For example, instead of writing in that particular fashion, I can also write like this. As you know, this can also be written like minus to plus infinity h of k x of n minus k. right? This is also done because the convolution operation is commutative in nature. So I can write like x of k h of n minus k or h of k x of n minus k. Okay. So if I follow the second one, in that case I can write the same expression as, let's start like h of minus 2 x of n plus 2 plus x of minus 1, sorry, h of minus 1 h of minus 1 x of n plus 1 plus h0 x of n plus h of 1 x of n minus 1 plus dot dot, right? Clear? So now the thing is that when you are finding out this y of n, and if the system is a memoryless system, then the value of y of n will depend only on x of n. It will not depend on x of n minus 1, that is the previous samples. It will never depend on x of n plus 1, which are the future samples. So it will depend only on x of n. So now, if you take a look at the expression over there, you see there, you have h of minus 2 x of n plus 2. So had this output been dependent on future samples, then this h of minus 2 should be non-zero. H of minus 1 should be non-zero if they depend on future samples. Similarly, if the present output depends on the past input, previous input, then this h of 1, h of 2, h of 3, h of 4 will be non-zero. But here the case is that the present output will depend only on the present input, neither on the past input nor on the future input. So therefore, all these will be irrelevant, all of them. This will be relevant, this will be relevant, this will be relevant, and all the other terms. Only this term will be there. Because these terms, h minus 2 x n plus 2, that means what? X n plus 2 is what? With respect to y of n, x n plus 2 means what? The future samples. X of n plus 1 is what? The future sample. What is x of n minus 1? The past sample. What is x of n minus 2? The past sample. But since the system is memoryless, so it will not depend on the previous or the future sample. It will only depend on the present sample. The present output is dependent only on the present sample, right? So it will only depend on h0. This y of n should be equal to h0xn. It depends only on this. Or in other words, you can see this h of n is basically a sequence, na? H of n. It's a sequence. So it can range from say minus m to plus m. But if the system is a memoryless system, if the system is a memoryless for an LTI system, if the system is a memoryless system, then this h of n is equal to 0 for n not equal to 0, and that is equal to non-zero for n is equal to 0. So just by observing the impulse response, you can check whether the system is a memoryless or not. Therefore, you can characterize the system from one perspective. From the perspective of memoryless, whether the system is memoryless or not, you can simply observe the impulse response and check whether this condition is getting satisfied or not. If the condition is getting satisfied, then you say that okay, the system is memoryless. If not, then the system is not memoryless. So what is the condition which needs to be satisfied? You have to check that whether h of n is equal to 0 for n not equal to 0. For all the positive and negative integer values for this, if h n is equal to 0 and z is equal to non-zero, any constant non-zero value, positive or negative, or n is equal to 0, then the system is a memoryless. So therefore, for memoryless system, this h of n, so can you relate any function for a memoryless LTI system? Impulse response. The impulse response of this LTI system, LTI and memoryless system. Impulse response of an LTI memoryless system is given by this particular thing. Na? So can you relate the function which you have already studied? Huh? Delta function. It's not exactly delta n, but a scaled version of delta n. So I can write h of n as some constant c times delta n, which exists only for n is equal to 0, and for other values of n it is 0. Right? So therefore, if the impulse response of a system is having a form of an impulse response, is having a form of a delta function, something like that, a scaled delta function, c times delta n, then you can say that, okay, the system is a memoryless system. If not, then the system is not memoryless. So from the perspective of having memory or not, so you are just observing the impulse response of the system, and based on that, you can say whether the system is a memoryless or not. Remember, the system has to be LTI format. Because if the system is non-LTI, then this output-input expression, this yn is equal to summation x k h n minus k, that expression is infinite, remains infinite. So this entire derivation becomes erroneous in that particular case. Next, we move to the second property, that is the causality. Right. Once again, let us write down the expression for y of n. The same expression, x of m h n minus m. M is ranging from minus to plus infinity, or h of m x of n minus m. M is going from minus to plus infinity. So let us explore one of those two summation. Which one to explore? Let us explore the second one. So let's write something like that: h of minus 2 x of n plus 2 plus x of minus 1, sorry, h of minus 1 h of minus 1 x of n plus 1 plus h of 0 x of n plus h of 1 x of n minus 1 plus dot dot. Now, if the system is causal, what do we expect from the system? The output will depend on past and present. Past and or present. Past and present, past or present. Right. So therefore, in this expression, the output must not depend on this. So y of n means what? The sample taken at time instant n. What about x of n plus 2? What about x of n plus 1? What about x of n plus k for k greater than 0? These are all future samples. So therefore, this y of n must not depend on x of n plus 2. Y of n must not depend on x of n plus 1. So how to ensure this? You can only ensure if h of minus 1, h of minus 2, h of minus 3, h of minus 4, all of these values are 0. Right. So they must not depend on this. It will only depend on this. and the subsequent values. So genetically what I can say, so if the system is a causal system, then the impulse response in the sequence you have this H0, H1, H2, H3, H4, they are present, they are non-zero. But H of minus 1, H of minus 2, H of minus 3, H of minus 1 and so on, they should be 0. So the final expression is H of n should be equal to 0 for n less than 0, and that is non-zero or 0, sometimes 0 also for n greater than or equal to 0. That condition has to be satisfied, this condition. This is the condition. The n should be, for n less than 0, h of n must be 0. Then only you can say that the impulse response is causal. And if the impulse response is causal, then the system is also. What does it mean? H of n is equal to 0 for n less than 0. That means impulse response is basically a sequence. And that's a causal sequence. So for a causal LTI system, the impulse response is also a causal sequence. Can you get the point? What is that? H of n is equal to 0 for n less than 0. And can be 0, can be non-zero, combination of both for n greater than or equal to 0. It must obey the cause and effect relationship. The impulse appears at n is equal to 0. You can't expect the impulse response to appear before that. Impulse appears at n is equal to 0. You can't expect that the impulse response appears at n is equal to minus 1, minus 2, minus 3, minus 4. That will disobey the cause effect relationship. Right? So h of n must be equal to 0 for n less than 0, and otherwise you can have any such expression for that. Okay, so now let's move to the third property, third very important property. That property is all about the Vibo stability, bounded input, bounded output stability. Whether I can check the system is Vibo stable or not just by observing the impulse response of the system. Once again, let us consider the same expression. Y of n is equal to summation x of m h of n minus m, where m is ranging from minus to plus infinity, or similarly you can have the same expression, m is going from minus to plus infinity, x of h of m x of n minus m. Okay. So what do we mean by Vibo stable system? For all possible bounded input, the output is also always bounded. So therefore, if the input is bounded, so I have to ensure that mod of x of n is always less than or equal to some mx for all xn. That means I have put some bound on the input, bounded input. Mod of xn is always less than or equal to some mx, and obviously this mx is less than infinity for all xn. Then this set of xn will give you, rather I should not write all xn, rather whenever I am referring with respect to signal, it should be for all n. It should be for all n. I am referring with respect to signal, so it should be for all n. For all n, mod xn should be less than or equal to mx. That means the system is, signal is bounded, bounded signal, bounded input. Okay. So I have to check whether the output is also bounded or not. Right? So what about your mod of y? Mod of yn. So as far as the formula is concerned, I can write, let's take the second summation, m from minus to plus infinity, h of m x of n minus m. Okay. Now this is what? This is basically the mod of a plus something in this particular form, mod of a plus, isn't it? Mod of a plus, we have like so many summation over there, and you know this mod of a plus b is always less than or equal to mod a plus mod b, right? So therefore this thing, this mod of y of n is always less than or equal to, so I take the summation outside, minus to plus infinity mod of hm, sorry, mod of hm x of n minus m, right? Mod of a plus b is always less than or equal to mod a plus mod b. Okay, and then let's take the another lemma over there. Mod of ab is equal to mod a into mod b. So this is less than or equal to m going from minus to plus infinity mod hm mod x of n minus m. Right. And you know this mod of x of n minus m, as you have already mentioned, if x of n, this signal, is a bounded input, this mod of x of n minus m or mod of x of n, whatever it may be, this is always less than or equal to mx. This is always less than or equal to mx. So therefore, moving forward, mod of yn is always less than or equal to mx, and then you have m going from minus to plus infinity mod of hm. Okay. Now I have to ensure that this mod of yn, if the output is bounded, that means what? This entire thing, this has to be less than or equal to some my, which is less than infinity for all n. This summation sign, this entire thing, this entire thing. Yes or no? Can we get the point? Now, how to ensure this? This mx, we know that mx is a bounded quantity. Now, how to ensure that this entire mx multiplied with summation m to minus to plus infinity mod of hm is also less than or equal to some bounded number m of y. So the only condition by virtue of this condition can be established is that this is finite. M going from minus to plus infinity mod hm is finite. One finite quantity multiplied with another finite quantity will give you a finite quantity. Or in other words, if the impulse response h of m, if this impulse response is absolutely summable, if the impulse response is absolutely summable, then I can say that the system is Vibos, then the entire system is Vibos stable. So once again, the Vibos stability criteria can also be judged from the impulse response first. Right. So all the properties of a system, like the memory-less or memory-based system, the causality, then the Vibos stability. So all these properties can be verified and can be checked once you know the impulse response of the LTI system. And that is the beauty of the LTI system. You have performed only one experiment. You have provided the impulse as your input to the system. You have calculated the impulse response. Calculate the impulse response, and then you know everything about the system. Whether the system is stable, whether the system is stable, whether the system is a bound, whether the system is memoryless or not. You know everything about the system. Right. So the thing is that impulse response. So if the impulse response of an LTI system is absolutely summable, not square summable, absolutely summable, then it is Bibo stable. Right? So although I have given the examples for discrete time system, you can also extend this idea to the continuous time system, for example. Same thing. That means for a continuous time system, this h of t must be equal to 0 for t not equal to 0, and that is some non-zero value for t equal to 0. Then the system is a memoryless system. Right? Similarly, h of t must be equal to 0 for t less than 0 if the system is a causal system. And summation and then integration from minus to plus infinity h of t dt will converge and will give you some finite value for a system to be Bibo stable. Yeah? Okay. So before I conclude today, I'm just asking a question. Let's investigate this particular system. Say y of t is equal to t times x of t. Let's try to investigate the system. Y of t is equal to t times x of t. You have noticed this system, y of t is equal to t times x of t. Right? So what will be the impulse response of the system? What will be the impulse response of the system? System is given by y of t is equal to t times x of t. Can you tell me the impulse response of the system? How to find out the impulse response? How to find out? The input and output relationship is given. Yt is equal to t times xt. Xt is the input, yt is equal to output. So how to find out the impulse response of the system? For any system, how can I find out the impulse response? Thing is that I have provided, I know that this is a formula. Xt is my input, yt is my output, and it follows this formula yt is equal to t times xt. That is my system. So what will be the impulse response? How to calculate the impulse response? How to calculate? Is it so tough? How can you calculate the impulse response? To provide the impulse as my input. Isn't it? Can you get my point? Yes or no? You're completely blank. I really don't understand. Can you get my point? What I'm saying? Right. And that is how we find out the impulse response. Name says that impulse response due to impulse, right? So just replace xt with del t. Just replace xt with del t and find out ht as y. Done. So what will be the impulse response then? What is ht then? T times del t. T times xt equal to t times del t. Yes or no? Okay. Now you tell me, is this system memoryless? Yes. Okay. How to check it's memoryless?
It is depending on your measurement.
Huh?
It is depending on your measurement.
From which expression? This expression? This expression, equation number 1 or equation number 2? Huh? 2, not from 1. 1 also. Both. Okay. Okay. Is it a causal system?
Yes.
Causal. Equation number 1 or 2? Both. Okay. Is it pivot stable? Is it pivot stable?
No, sir. No, sir.
No. Why not?
Because when t tends to infinity, it also tends to infinity. Output is not bounded. Output is not bounded.
Output is not bounded. Now here is a fallacy. Now here is a fallacy. You have got ht is equal to t times delta t, right? That's why I asked you equation 1 or equation 2. That's why I asked you, okay, memoryless, both. You told them both. Memoryless, okay, from 1 and 2, we can verify that okay, it's memoryless.
From 2 it is Vivo stable.
For Vivo stable, for causal, okay, 1 and 2 both. But when it comes to Vivo stability, then if you take a look at the second expression, and if you just find out this summation, I mean, if you find out this one, na, minus 2 plus infinity, this one, h tau mod h tau d tau. This seems to be convergent. If you go by this formula, then whether the system is, I mean, the impulse response is absolutely summable. From that perspective, it seems that okay, the system is Vivo stable. But if you provide the input x of t as say a step function u of t, suppose instead of providing x of t is equal to delta t, if you provide x of t is equal to u of t, then you'll see that it will diverge to infinity when t is equal to infinity. So from one perspective, it gives you the a false notion of having a Vivo stable system. From another perspective, it will give you the different notion. Right. So here is the confusion. But where is the fallacy? Can you tell me where is the fallacy?
The second one, the input is only unbounded.
No, delta is not unbounded. It's existing only for t is equal to 0. Input is not unbounded actually. Or you can also consider okay, y is equal to n of x. Take the discrete counter from x. What is the fallacy? Where is the fallacy? Fallacy lies in the fact that our entire discussion is made on the assumption
It's time variant.
the system should be LTI. Right? System should be LTI. Linear time invariant system only you can check this. But check this yt is equal to t times xt or yn is equal to n times xn. This is time variant system. But if you have a time variant system or nonlinear system, I mean if you have a system which is non-LTI, then just by finding out the h of t or h of n and finding out this absolute summability and absolute integrability, you cannot decide whether the system is a reversible system or not. Can you get the point? Yn is equal to n times xn or y is equal to t times xt itself is a non-LTI system. So if you now find out the impulse response, you'll see that the impulse response is absolutely summable. But that doesn't characterize the system to be a reversible system. Because if you provide some other input instead of giving some impulse input, if you provide some step input, the output will be unbounded. Okay, so that's why I have given this particular example to make sense that this absolute summability or absolute integrability of impulse response to find out its reversibility is applicable if and only if the system concerned is a LTI system, is an LTI system. If not, then you should not go by this one. And you can't say whether the system is, I mean, if the system is non-LTI, then it is not just possible for you to check whether it's a stable system or unstable system, just by observing the impulse response. LTI system will give you that extra facility. Only one experiment that will characterize the whole system altogether. Otherwise, not possible. Okay. Okay, so with this, we have hopefully have come to the end of this unit of your course. That means we have already completed the third unit, first, second, and third unit, and then in the next class we will move to the some other perspective of the signals, of looking the signals from different dimension, not from this particular angle, but from some other angle. Some series explanations and some transformations and all. Hopefully you have not studied this, no? Fourier series, Fourier transformations you have not studied. So from the next class onwards, we will observe the signal. First we will observe the signal from that particular perspective, not from this perspective, but from another perspective.